Okay, let's spend a little time talking about oscilloscopes. And an oscilloscope's a measuring instrument. It doesn't create a waveform. It only measures the waveform or the output of something else. So it's just a meter in the sense that it's reading um, um, what a different piece of equipment is outputting or what a circuit's outputting or whatever the case might be. So um, don't think that it's changing the signal. It's just changing the view of our signal that we have. What you're looking at here is pretty much a general view of a oscilloscope. This is the old analog type. Mostly what you encounter, there are digital versions out there. They're a little more expensive. They're a little more feature rich. So it just kind of depends, but where you're at. But if you take a look at this, it talks about the vertical and the horizontal right here, and we'll be getting to those. But notice, because there's a channel 1 and here's channel 2 on this one, there's a setting for channel 1 for the vertical and channel 2. So those are independent of each other. But the horizontal, which is our time or frequency or period, they all relate to one another, affects both channels. So we can only deviate the vertical for independently for each channel, but the horizontal has to remain the same, and that'll get a little more clear as we discover what that is. So obviously we use these to analyze and troubleshoot AC circuits. AC can vary. It is an alternating current. It can vary in frequency, anything from 60 hertz like we use in our home to in the megahertz on computers, and now in the gigahertz. So we're starting to see some very, very fast signals. Most of our oscilloscopes in here are probably up to 100 megahertz, so we don't have anything capable of measuring something in any greater than that. But anyway, let's move on. So just as a doctor uses x-rays to look inside of a patient, we use this to look at circuits. It can see things that just an ordinary handheld digital multimeter cannot. And that's why we use oscilloscopes. And we're going to first look at an analog and talk about it. And it is a piece of test equipment. And again, it's a measuring device. It just as if I'm using an x-ray to look inside my body, I'm not changing what's there. I may zoom in or zoom out using that piece of test equipment to see something in the body, but what's in the body is in the body, just like what's on the board or piece of equipment that we're analyzing with this oscilloscope. We're not changing it. We may change our view, but that signal remains just as it does with or without the oscilloscope hooked up. And it can measure amplitude, which is voltage. That is the vertical that we talked about. It's independent on each one. And it can measure period, which is time. And of course, we can see the different types of waves. So when we talk about amplitude, that's top to bottom. That's how basically the voltage reading of the signal, the just like we measure DC with a meter, we can measure millivolts all the way up to kilovolts if we happen to have something that goes that high. This is the amplitude of the AC. Now the period is actually the inverse of frequency. It's how often frequency is how often something occurs. Period is what one waveform occurs in. So if you look, this is one entire sine wave. We're right here at the middle line. We're rising, we're falling, we're coming right back to the middle line, and we're going to repeat that. So so that is period. And of course, just the shape is the general shape. We can get a whole lot more out of it, but that's what we're going to talk about for now. We'll get to it a little bit later. So the display just lets us see, and this is an old CRT display, so the scope's been around a long time. They use these CRT displays, and they work very well for that. And Cathode ray tube, again, used to see these now probably in flat panels, but these are the old CRT tubes. And we call that waveform a trace. So when you hear somebody say, what kind of trace did you have on your scope? That's what they're talking about. What did that waveform look like? And if you take a look, oddly enough, you would think this thing would be square, and it looks square when we look at it. But there are 8 squares high on this particular one, and we're talking about the large squares, not these little tick marks up here. 1, 2, 3, 4, 5, 6, 7, 8. But there are 10 wide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each one of those is called a division. And when we're looking at the settings on the scopes, we're talking about those major divisions. Again, not these little tiny tick marks, but they can be used to give us some good estimates when we're using the scope. And it says to aid in accurate measurements, each division of 1 square centimeter is also split equal into 5 subdivisions of 2 millimeters each. Now you really don't have to know that's a centimeter, and you don't have to know that's 2 millimeters, but the idea is to help you understand what's going on here. So let's look at this. So if we look at this one, times per division is 5 milliseconds. And remember, time is left to right. So we can get the period of this waveform with the full sine wave just by counting blocks. So each block represents 5 milliseconds. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So this particular one is 50 milliseconds wide. Well, frequency is the inverse of that. And all we'd have to do is calculate it. So let's bring up my handy dandy calculator if I can get it to come up here. Yeah, my recorder is in the way. Actually, I can go off screen. Hang on just a moment. Calculator, we'll bring it in. So we did 5 times 10, which was 50 milliseconds. And I remember milli means 1/1000, so we have to divide 50 divided by 1,000. And that gives us 0.05 seconds. So the inverse of that, or if we divide that into 1, or if we reciprocate it, this particular calculator has a reciprocal key, then we find out that this particular signal is 20 hertz. It occurs 20 times per second. The reciprocal being the period, which is 50 milliseconds that we see here. So I don't know if it skipped. It does. And it goes on down and tells us all that, 50 milliseconds. And it doesn't do the math and talk about the frequency yet, but we'll get there. And notice, as it says, there's only one of these. Both channels share this time. We can't reference time for one thing and reference time for something else. We have to have those in sync. So when we see 2 different readouts on our oscilloscope, they're both using the same time per division. They may be using different volts per division. This guy might be 5 volts per division. This bottom guy may be a few millivolts per division. They may vary widely in their amplitude or voltage value, but the time is going to be the same for both. And so that's pretty much fixed. And I'll let you read these here. But each channel does have its own independent. Notice this particular one, channel 1 is set to 0.1. Channel 2 is set to 5 volts per division. So we can do the math there when we're talking about major divisions. If this is channel 1, I don't really know which one is which, but assuming the top one is channel 1, that would be, from here, would be 0.1, 0.2, 0.3, 0.4 volts total amplitude. Down here, if this is the 5 volts per division, that would be from the bottom 5, 10 volts. So quite a bit of difference between 10 volts and 0.4 volts, but we have the ability to independently set the amplitude. Now again, whatever is producing this signal, we're not changing it. I could change this guy right here to 2 volts per division, and he would take up all 10 of these blocks, because it would be 2 volts per division. If he's 10 volts, would be I said 2 volts. I said all 10, excuse me. It would be just 5 he's on 5 volts per division, he's taking up 2. But if I put him on 2 volts per division, he would take up 1, 2, 3, 4, 5. So he would take up more than what he's taking, but he's still 10 volts. 5 times 2 is 10, 2 times 5 is 10. It's still 10 volts, so no difference there. And of course, the bigger we get it, the more accurately we can see it. Using a scope, it's fairly subjective. You know, both of these are showing 8 volts per 8 volts peak to peak, and when we say peak to peak, we're talking about the high peak to the low peak, or the low peak to the high peak. It really doesn't matter. But I can tell this is 8 much easier because this is 1 volts per division. I can go 1, 2, 3, 4, 5, 6, 7, 8. Than I can at 5 volts per division, because I'm having to, I know it's not quite 10, and I know it's way more than 5, but I might end up with 9 or 7. But here I can pretty well subjectively say that's at 8 volts now, maybe at 8.1 or 7.9. But I can see a lot more clearly than I can over here on the right hand side. So that's why we need to use those volts per division like we do. So the positive cycle is anything that appears above the 0 line. The negative cycle is anything below the 0 line. And that's where we get peak to peak, positive peak, negative peak. And we have to have one complete cycle. Wherever we begin, we're rising to a peak, we're falling to a negative peak, and we're coming back up to the center line, which is where we begin. The next one would be over here, and we'll just keep cycling if we saw that continuously. And says the waveform cycle start and stop on a reference line, so we like to use that 0 line there. And talked about peak to peak already, high peak, low peak. Should be sinking in by now. And a single peak is half of the peak to peak. It's the 0 line either to the positive or the 0 line to the negative. But that is a peak value, so peak is equal to 1/2 of peak to peak. So pretty easy math there. That shouldn't elude anybody at all. So again, highest to lowest for peak to peak, or highest to midline for peak, and midline to lowest on the negative for the negative peak. So peak plus peak gives us peak to peak. So there you go. All right. So oscilloscopes display the entire voltage waveform. Multimeters measure voltage in root mean square. To convert peak to peak to RMS, use the formulas below. And if you actually were to measure a waveform out of the AC line in your home or here at the school, you would measure a higher voltage than 120 volts, because 120 volts we talk about is the RMS value. And to get that RMS, we have to take the peak and multiply it times 0.707 to give us the RMS. So it's a reduced value. So the peak to peak would be even greater than that. We could do some backwards math and get it. But this 120 that we're reading is actually dividing this in half and then multiplying it by 0.707. So quite a bit of reduction. So the peak to peak value of our AC home voltage is much higher. And they can also measure DC. And if we have our trace centered on the reference line, and most times we will, DC is going to be a straight line. It's direct. There's no alternation to it. It is a direct voltage, and we just have to count the voltage in relation to that reference line. And I think we're about to run out of time on the video. This is just showing us, I'll finish this slide up, it's just showing us that we have a positive voltage with reference to the reference line. That's a positive DC. Anything below that reference line will be a negative DC. So this is talking about DC, and we can measure that. Next, we're getting back to the AC. You notice AC is alternating, DC is direct current, and so there's no alternations to it. So this is a good point to stop, and I'll bring the video back at this point when we start again. And as always, if you have questions, you should know the drill by now. See your instructor. Thanks.